In section 3, day 1, we did systems of inequalities in which both of those were straight lines in the linear function family. And today, we're going to mix them. We're going to have one linear and one absolute value. So I'm going to do the same thing that I did before. I'll do them in 2 different colors so you can see what's going on. This top one I'm going to do in red. It's a line. It's very important that you know the difference between lines and absolute values. It's not a V-shaped graph because it doesn't have the absolute value bars. And it is ready to be graphed. It's a line that crosses at positive 2. From there goes up 1 and to the right 3 a few times. Before you draw it in, take a look. It is dashed. So make sure you dash the line. The shading on this one is less than, so I'll try my best to show you what that means. Less than means go to the y-intercept shade down, so that ends up being all of this area here. For the second one, this is an absolute value. It's a V-shaped graph because of the absolute value bars. It has moved right 5, but not up or down. So I'm going to start by moving my vertex over 5. From there, I'm going to count off that A value, that stretch, that compression. There is no stretch or compression. Remember, that's the number that should be right there, which means it's understood to go up 1 over 1. So I'll go up 1 over 1 a couple of times on this side, then go back to the vertex and go up 1 over 1 a couple of times on that side. And before you draw in the V, it is also dashed. So when we first started talking about graphing, I said it's super important for you to take these lines, even if they're absolute values, all the way to the end of your graph, because that helps with shading. This absolute value function is a greater than, so put your finger on the y-intercept shade up. You end up shading all of this. The section of which they overlap occurs right in here. That's the solution to the system of inequalities. So this isn't done any differently than the lines that we did in the section before. It's just that one of them will consist of an absolute value graph. Letter B, 2 of them again. This top one I'll do in red. Because there's just a y is less than 0 is actually a straight line, not diagonal like you're used to. It's also dashed because there's no line underneath the inequality. It happens to fall right on the x-axis. And those values that are less than that shade down. For the second inequality, that's an absolute value that has moved down 4. So I'm going to start by placing my vertex down 4. And from there, count off my stretch or compression, which is understood to be a positive 1. So positive 1 a couple of times on the right, and then up 1 over 1 a couple of times on the left. This line ends up being solid for the absolute value function because there is a line underneath. And it's a less than or equal to, so I want to shade below the V. So you should find that these intersect below both of them. Oops, went up a little bit too far right there. Let me erase that. Right there, can't be there. So it's everything below the V and below the line. Make sure that whatever color you anticipate to be your final color is darker than the other two. All right, problem 1, letter C, is different than the others because it's not in a graphable state. If you take a look at the first inequality, 3x minus 2y is greater than or equal to 2 is not ready to graph. I'm going to start by subtracting 3x from both sides. Leaves me with a negative 2y is greater than or equal to negative 3x plus 2. And divide everything by a negative 2. Be really careful, that sign, that greater than or equal to, turns into a less than or equal to, and then a positive 3 halves x minus 1. So that's what I need to graph. That's a line. No absolute value bars, means it's just a line. It crosses at negative 1, and from there goes up 3 over 2. It is a solid line. The shading on this one is less than. Be careful, it was a greater than, but we flipped it when solving, so less than shades below the line. The second inequality is all ready for us to graph. It's an absolute value. That absolute value has moved down 1, right 1, and has been reflected. So let's take care of the down 1 and right 1 first. Down 1 and right 1 puts my vertex right there in quadrant 4. Now that reflection means that instead of counting up and over, I'm actually going to count down and over. And when I draw the line in, it's going to be dashed. Sometimes I think the trickiest part of these questions is ignoring whatever is on the graph for the first inequality in order to complete the second. Now, that absolute value inequality needs to be shaded as a greater than. So I want everything that's above the absolute value inequality. So if you take a look at the overlap, that occurs right in here. Make sure that that overlapping section is darker than the others. All right, letter D, same thing. If I take a look at this top inequality, it is not ready to be graphed, so I'm going to start by dividing both sides by 5. I get y is less than 3/5 x. That's a line, no absolute values, it's a line. It starts at the origin, goes up 3 and to the right 5. And when drawn in, should be dashed. The shading on this is less than, so everything below it. The second inequality is ready for us to graph. It's already by itself in terms of y. It is an absolute value. It has not moved left, right, up, or down, so it's going to start at the origin. But from there, its slope is a -2. So down 2 over 1 on one side, then go back to the beginning, go down 2 over 1 on the other side. And when you draw it in, it should be solid. For the shading on this one, you want less than. So y-intercept and down. These two overlap in what looks to be like a Christmas tree. Pause the video and do the you try it. All right, problem 2. You're supposed to identify the inequalities for which each ordered pair is a solution. So all they're asking you to do is to look at the graph. If the ordered pair falls in the shaded region, it's a solution. So we're going to start with letter A. I'll do this one in red. 0, 0 is right here. It is in the shaded section, so the first graph works. In the second graph, it's also in the shaded section, so it works. And in the third graph, 0, 0 is in the shaded section, so it works. That's what you're looking for. If it's in the shaded area, it works. Letter B, I'll do in green. 2, 8. 2, 8 is right here. It's not in the shaded section, so it is not a solution. In the second graph, 2, 8 is right there, so that one works. And in the third one, 2, 8 is right there, not in the shaded section, so it doesn't work. Letter C, I'll do in blue. -1, -9 is right there, so it is in the shaded section, it works. In the second graph, -1, -9 is right there, it does not work, it's not in the shaded area. And in the third graph, -1, -9 is right there, so it works. The last ordered pair I'll do in purple, 6, 0, 6, 0, 1, 2, 3, 4, 5, 6 is right there. In the first graph, 6, 0 occurs on the line. This is really important. If it is on the line and the line is dashed, it is not a solution. If it is on the line and the line is solid, it is. Because this is dashed, it is not a solution. If you look at number 2, 1, 2, 3, 4, 5, 6 is right there, also not a solution. And the third graph, 1, 2, 3, 4, 5, 6 is right there, that one is. An ordered pair is a solution to the system of inequalities if it's in the shaded region.